Rivers are characterized by fairly steady, unidirectional water flow, and that process is responsible for sediment transport and for the generation of predictable features called bed forms. The present is often said to be the key to the past, so in this lecture we'll consider how sediment is transported in modern rivers. In upcoming lectures, we'll look at the types of sedimentary structures and then use them to infer the processes that were operating in ancient depositional environments. Moving fluid, we're considering water here, but this could equally apply to air, transport sediments with two main types of motion. The sediment can move along the riverbed by sliding or rolling or bouncing in a process called bed load transport. The rolling and sliding motions are traction, and the bouncing is technically called saltation. Other sediment is carried in the suspended load, and suspended means that it's continuously floating in the water column without touching the bottom. That can happen simply because of turbulence, the swirling motion of the water itself, or it can happen due to grains colliding with each other. That produces something called dispersive pressure. As we'll see shortly, the suspended load tends to be finer grained particles like clay or silt, and the bed load tends to be coarser particles like sand or gravel. So grain size is a fundamental piece of information, and we're going to use it again and again to infer ancient depositional conditions. So we'll first discuss what controls grain movement, overall, but especially during bed load transport. The next set of slides will introduce some bed forms produced by unidirectional water flow. These bed forms, or at least the sedimentary structures that they leave in the rock record, are also extremely useful for diagnosing ancient environmental conditions. And in class, you'll work on determining how grain size and water velocity affects the formation of different bed forms. Let's first consider the factors that control whether a sediment particle will move in a water flow or whether it won't move in that water flow. Well, think about this spherical particle sitting on the bed. The blue lines you can see are luminescent particles moving through the water. So this larger particle, the spherical particle, will move if the forces that promote movement outweigh the forces that hinder movement. And it will sit still if the forces that are hindering the movement are greater than the forces trying to push it to move. So what are those forces? Well, the main force opposing movement is simply the force of gravity. Fluid drag, which is caused by the water flowing over the surface of the grain, is the primary force trying to move the particle. There could also be a lift force that will help movement, which is caused by because the water velocity, shown in the contours of U on the right-hand diagram, is slower below the particle than it is above it. You can see the sort of green and blue below the particle and the yellowish above the particle. Slower velocity means higher pressure, so the particle will feel some lifting force because of that pressure gradient. The sediment particles, of course, are also not isolated. They're sitting there touching other grains on the bed. So there can also be friction and electrostatic forces from static charges that tend to hinder motion. So for simplicity, we'll consider just the two major forces, gravity and fluid drag. So gravity is inertia. It's a resisting force that must be overcome for the particle to move. It's simply the mass of the particle times the gravitational attraction g, or the acceleration due to gravity g. But grain mass is kind of a little awkward to work with. We typically think more about sediment in terms of its size more commonly. So we can just replace that mass term with volume times density. So volume is, of a sphere at least, is 4/3 pi r cubed, and the grain density is rho. And so we could also just bundle all these constants into a term and consider d instead of r. So we want to think about the particle diameter instead of the radius. And from this final equation, you can see that the larger the particle is, the larger the d is, and the denser it is, the more inertia it will have, and the harder that particle will be to move. So the force that tries to push the particle into motion is dominated by fluid drag. The kinetic energy that's transferred from the water to the particle as the water flows over the grain is given by this first equation. So I've already replaced the mass of the fluid by the volume V times the density rho, and velocity here again is given by U. I'm not sure why U is used instead of the more familiar V that you might remember from physics classes, but that's just the way it is. Energy is defined as force times distance, so we can convert this energy into the moving force, which is kind of what we care about, by dividing the volume by the particle diameter, the distance over which the diameter being the distance over which the water flows. So this gives us then, and the force is just the area times the density of the fluid times the velocity squared. And we want to think about particle diameter, so the area of the particle, at least in a sphere, is just proportional to its diameter squared. We'll take all the constants and bundle them up into this term again. So again, as you can see from this equation, the final one here, the force from the fluid drag will be greater on larger particles when d is bigger and when the water is flowing more quickly. So at the exact moment when the particle just starts to move, these two forces, inertia and fluid drag, will be exactly balanced. You can think about this because if the inertia is bigger, the particle won't move. If the drag is bigger, it will. So the particle just starts to move when those forces just become equal before drag gets bigger. So we can write this mathematical equation here, which just takes our two previous equations and says that they're equal to each other, and then rewrite that just using some algebra to figure out this term u star called the critical velocity, which is the velocity necessary to move a particle of a given size and density. So we can even simplify this a little bit, as we'll see in the next slide too, because for typical river conditions, this constant term is around 0.06. That number is determined just by trial and error through experiment. And because the fluid density is approximately 1 gram per cubic centimeter, we don't have to divide by the density of the fluid, so the equation can be simplified like this. This equation describes something called Shield's criterion, and that is the maximum particle size, d, diameter, that can be moved for a given current velocity u. That is called the competence of the flow. A given water flow can move particles smaller than a specific diameter, but particles larger than that diameter won't be transported. We can also illustrate this graphically with this Hulstrom diagram, but you might notice that the relationship really only holds well at grain sizes bigger than 1 millimeter, at least for erosion. Deposition tends to behave quite nicely throughout. So why is this happening? Well, initiation of grain motion can actually be difficult for these finer grain sizes because we ignored the other terms. Right? We just considered fluid drag and inertia. We didn't consider lift, or more importantly, we didn't consider friction and electrostatic charges. So the relationship, at least for erosion, doesn't really hold at these fine grain sizes because of friction. The particles, especially if they're compacted together, might have a lot of friction, and electrostatic forces, which may be especially important in clay minerals, these platy minerals that have charged surfaces. Once those fine particles get moving, however, they're really easily transported, and so they're not going to be deposited until water velocity is extremely slow. You can see that, for example, 1 millimeter grain will be deposited once the water slows down to approximately 10 centimeters per second, but a 0.1 millimeter grain won't be deposited until the current velocity is approximately 1 centimeter per second. So given the importance of current velocity on controlling the competence of the flow, which is the largest particle it's able to move, fluctuating velocity can result in alternating erosion or transport and then deposition. So for example, let's consider a flow that starts around 5 centimeters per second. So this is sufficient to transport grains smaller than medium sand, say half a millimeter, but anything larger than that won't move. So if this river floods, the current velocity increases. Now the formerly stable coarse sand and very coarse sand, and even some of these granules, they weren't moving before, well now they get mobilized and now they start moving. Well, once the flood subsides and the velocity decreases, now we're going to deposit all that coarse material, and even some of the medium sand and everything bigger than, say, 0.1 millimeters, because the flow is no longer strong enough to move it. So this fluctuating velocity and the importance of water energy on transport and deposition is the main reason why sedimentary rocks are layered. And this is going to be, you'll see this in the field trips, you'll see this throughout, that sedimentary rocks are layered rocks. And that layering arises because of changes in energy levels.